Means, medians, modes, variances, and standard deviations. It's time to take a look at measures of central tendency and variability. This is Totally Doable Stats. So let's go ahead and take a look at those measures of central tendency. We're going to start with a basic data set. We will take 1, 2, 3, 3, 4, and 5 as our data set. For those three different measures of central tendency, we're going to be looking for a mean, a median, and a mode. So let's just work from the bottom to the top, since that's kind of the easiest thing to do. The mode is simply the one that occurs the most. And since we have 3 twice and all the other ones only once, that means our mode is 3. And it's just that simple, where we can go through and see that. If I want to find the median, what I'm actually going to do is figure out what is the middle number as they've been put in order from smallest to largest. So in my data set, where I've got 6 numbers here, if I count in 1, 2, 3 from the left, this is the one coming that way, 1, 2, 3 from the right, you'll notice I don't exactly have a middle number. And so in that instance, when I'm calculating the median, I take those 2 numbers in the middle and I find their average, which we can do by sight on this one. The median is also going to be 3. And so if it's an odd numbered data set, that's a little easier. It's just the number that's exactly in the center. We'll maybe take a look at that in a second. The mean is the one you actually probably were the most familiar with to begin with. And if I'm going to write out the actual formula for the mean, that means when I calculate the mean, that is the sum, and so I'm going to use a capital sigma to signify sum, of all of the points in the data set, and so we'll just call that x, divided by the number of data points that I have. So for this data set, it's going to look like this. The mean is going to be 1 plus 2 plus 3 plus 3 plus 4 plus 5, all divided by n. I've got 1, 2, 3, 4, 5, 6 pieces of data, so 6. Pretty quickly, I'm going to see that that gives me, let's see, 1 and 2 is 3, 3 and 3 is 6, that's 9, 4 and 5 is 9, so that's 18 divided by 6. My mean is going to be 3. And by the way, the symbol for mean, while this is the formula for the mean, the symbol for the mean is going to depend on whether I'm talking about a population or a sample. If we're talking about a population, then I'm going to use the Greek letter mu, lowercase mu, and that is going to be my symbol for the mean. And so again, here my mean is 3. But I want to show you real quick what happens if we have an extra piece of information added in, and that extra piece of information is weird or different from what we've had. Let's see if we can make this an example. Up here I've got this data set, 1, 2, 3, 3, 4, and 5, and let's assume that each one of those numbers represents the value of a car and a neighborhood by tens of thousands of dollars. So this is a $10,000, let's say it's a Ford Fusion. This is a $20,000 used, maybe Ford Escape. Here are a couple $30,000 pickup trucks. Somebody got a nice $40,000 newer SUV, and somebody went and spent about 50 grand on a Cadillac Escalade. And if I wanted to know, driving through that neighborhood, what the average car is worth, the average car, according to what we just calculated, would be worth about $30,000. And that seems right from this data set. But what if somebody new moved into the neighborhood? What if, they still have the $10,000 car and the $20,000 car and a couple of $30,000 trucks and a $40,000 vehicle and a $50,000 Escalade, and somebody new moves into the neighborhood and they have just inherited a nice $170,000 Ferrari Testarossa from their very rich uncle who passed away. What happens then to my mean, my median, and my mode? Well, now I've changed the data set. I have 7 data points instead of just 6. If I start again from the bottom, my mode, well, I only have one number that's there more than once, so my mode is still 3. My median, now I have an odd numbered data set, so I'll have a true median just represented by a number. If I come in 1, 2, 3, 4 from the left, and 1, 2, 3, 4 from the right, that tells me my median is also 3. So we've changed the data set, but these haven't changed at all. But when we look at the mean, now all of a sudden, the mean is going to be 1 plus 2 plus 3 plus 3 plus 4 plus 5 plus 17, and now all divided by 7 because I've got 7 data points in here. And so when I add all that up, well, the 1 through the 5 there, that added up to 18, and so 18 plus 17 is going to be 35 divided by 7. Our mean, represented by mu, is now 5. So where the median car value is $30,000, the average car value has now all of a sudden changed to $50,000. But all we did was add one car. And so I show you this to help you understand what happens when we add an outlier into the mix. When we add a number that is radically different from the rest, it will affect the mean, but it will not affect the median in the same way. And so if we're talking about house values in a neighborhood, if we're talking about automobile values in a neighborhood like this, and there's plenty of other opportunities to think through something where you might have an outlier introduced, I want you to understand an outlier will affect the mean. It will not, however, affect the median and the mode in the same way. So one last thing to consider, maybe just as another example of the mean. Let's pretend that we have gathered scores from an exam in statistics classes, and we wanted to know what the average score in elementary statistics was on exam 1 across all the classes. And so we know that, let's see, Dr. Truscott teaches a class, and let's assume his class averaged a 74 on the exam, and Dr. Kilpatrick teaches a class, and let's assume that her class averaged 78 on the exam, and we know that I'm teaching a class, and so let's assume that I lucked out and got all the awesome students, and you guys averaged 85 on the exam. If I wanted to go through and figure out what the average score of SBU students was, could I just go through and add those up? 74 plus 78 plus 85 and just divide by 3. Could I do that? That would give me 237 over 3, which means the average score on the first exam was 79%. Makes sense, right? Kind of. It makes sense if all of our classes are the same size. But what if Dr. Truscott's class only has 10 students in it, and Dr. Kilpatrick's class only has 16 students in it, and I have a full class with 24 students in it? Does that make a difference? And looking at it, it seems like it should if we have different class sizes. And that's where a different formula comes in, where we calculate what is called the weighted mean. We're going to go through and figure out what the actual average is based on the fact that there are different size n's, different numbers of people in each of those classes. And it's going to require a couple of extra steps, because when we calculate the weighted mean, the formula for the weighted mean is the sum of scores in each individual group for however many groups there are, and so we'll say up to the sum of scores in group N, divided by how many people are in each group, all added up. Like this. When we go through and determine what the weighted mean is, we're going to have to go back and figure out, okay, so what was the total score in each class? And to do that, we know that the average formula for the average is the sum of x over n, right? Well, for Dr. Truscott's class, we know that the average was 74, and that average would equal whatever the sum of all the test scores is in his class, so we'll just give that an x sub t, divided by 10, because there were 10 students. So I would work that backwards. I would multiply 10 times 74, and that would tell me that the sum of all the scores in Dr. Truscott's class would be 740. If I do the same thing for Dr. Kilpatrick's class, where she had 16 students, that would tell me that the sum total of scores in her class, all added up, was 1,248. And likewise, if we go for my class, where the class average was 85, I know that the sum total of scores from my scores divided by 24 is how I figured that out. So when I multiply the 24 times the 85, I find out the sum total of scores in my class was 2,040. So now, if I go back here, take these pieces of information and calculate this weighted mean, that tells me the weighted mean is going to be 740 plus 1,248 plus 2,040 divided by all the numbers added up from each class. And so there were 10 students in Dr. Truscott's class, 16 students in Dr. Kilpatrick's class, and 24 in my class in this fictitious account. That would give us 4,028 divided by 10 and 16, and 24 is going to be 50, which means when I actually divide that out, I had originally thought by my shortcut method that the average score for SBU students in elementary stats on exam 1 was 79%, but I would find out that it's actually 80.56 or 81% if we round, meaning the average score wasn't a C, it was a B when I account for the number of students in each class. This is why we have to do weighted means. I've got to account for differences in class size to be accurate. Hopefully, as we've computed these, you've found that they're not that hard. They're actually fairly easy, which is why we call these totally doable stats.